So let's see how we really model solids. So imagine we have some mass m, and we put it on top of just kind of a square rod. Okay, so the rod is originally length L, but then after placing the mass on it, it's going to be squished by some distance delta L. Okay, so Young's modulus tells us that the force over the area being applied, which in this case would be mg over a, is equal to E, Young's modulus, times delta L over L. And E is really just the stress over the strain. This is something that might be talked about. Well, this would be talked about if we were in the engineering section, but this isn't specifically something I expect you to know. But we're just going to be looking at these principles of oscillations and of springs forces to derive this more complicated realistic spring force that's Young's modulus. Okay, so let's see how we can derive this with things that we already know. Well, let's define D, capital D, as the distance between the atoms in the rod. Okay. Then we see that L is going to equal m, the number of atoms stacked on top of each other, times d, the distance between them. Or in other words, the number of atoms that we have in series is going to be L over d. Now similarly, if we call A this cross-sectional area of the rod, we see A is going to be the number of atoms in parallel times d squared. Or in other words, N is going to be equal to the number of springs in parallel for each layer is going to be A divided by d squared. Right? And d squared because, essentially what we have is we have a lattice here where we're just saying we have a bunch of atoms. We're kind of making the atom square. So this isn't, necessarily the best approximation, but, we're assuming square atoms. And so if we have a d by d, that's going to give us an area A. Okay? So now let's put together the last two videos. So we see that K effective is going to be the number of springs in parallel, N, divided by M, the number of springs in series, times K. And so there would be some, effective spring constant K for these particular atoms. Well, this is just going to be A divided by d squared over L divided by d times K. So this is just going to be AK over LD. And so now we see that the force over area is K effective delta L. Well, this is going to be K over D delta L over L. So in other words, L. So in other words, Young's modulus, E, is just equal to K over D. So for this particular rod, in this approximation, we see that Young's modulus is just the spring constant between these atoms, and D, the distance between them. So we see that we started out with a very simple theory of just, a bunch of massless springs. And in just a couple steps, we're able to derive something that's actually fairly accurate and close to being, physically realistic.